Hello, my name is Annalise Kamir, and I will be presenting on my research project, Assessing Water Quality Resilience by Utilizing Pressure-Dependent Demand in Water Distribution Systems. So drinking water distribution systems are an integral part of our daily lives and a critical infrastructure sector in the United States. Disturbances in these systems are not only inconvenient to consumers, but can have drastic health impacts if drinking water becomes contaminated, disinfectant levels drop, or water ages beyond acceptable limits. It is important that engineers can predict how drinking water systems will behave in a variety of circumstances. However, due to the complexity of systems, which can serve hundreds of thousands of people, computer simulations are usually necessary to handle the heavy load. My research is focused on exploring the capabilities of these hydraulic simulators and ways to make them more reflective of reality. For the purpose of this project, an artificial distribution system was used. L-Town is an artificial water distribution system, the technical details of which can be seen in the bottom right corner of my poster. To simulate L-Town, I utilized the Water Network Tool for Resilience, abbreviated as WINTER, a free software package for Python. WINTER runs two hydraulic simulators, an in-house simulator and the EPA Network Simulator based on work done by the Environmental Protection Agency. WINTER Simulator can run pressure-dependent demand systems, varying water usage based on system pressure fluctuations, but it cannot run water quality analysis, which EPA NATE Simulator is capable of. Pressure-dependent demand is more realistic, tends to reflect system changes, and does not remain static. My research focuses on integrating these hydraulic simulators to investigate water quality in distribution systems undergoing changes in demand due to system pressures. By creating a framework to synergize WINTER and EPA NET, we can make our models more realistic and hopefully improve existing water distribution systems. I began running a hydraulic simulator in L-Town, and 24 hours after beginning, I introduced a disruptive event in the form of a pump outage. The pump was turned off for 3 hours and turned on for the rest of the simulation. At the top of the results section, you can see Figure 1. This figure shows what the water age in seconds is at all the nodes in L-Town if the system were left alone to run normally. High water age is denoted in red and is generally undesirable. As expected, there are not really any changes in the system over time. For the first run, I used EPA NET Simulator to illustrate a demand-driven system. In this system, demand was not affected by changes in pressure, and the results can be seen in Figure 2. Figure 2 shows 4 instances of L-Town during the simulation. The first image on the far left shows L-Town at 11:55 p.m., 5 minutes before the pump shut off, which is indicated by the red star. The second instance is at 12:05 a.m., 5 minutes after pump shut off, and already the water age in the middle part of town can be seen increasing as shown in the blue circles. The third image shows the 5 minutes after the pump was recovered at 3:05 a.m., denoted by the green cross, and close investigation reveals the disruptive system has a slightly higher water age. The fourth image shows L-Town at 3 p.m., 12 hours after the pump was turned back on, and the systems are now behaving similarly. To compare what would happen if the systems were running under pressure-dependent demand, I first used the WINTER simulator to run the hydraulic simulation, then transferred the data to the EPA NET simulator and ran a water quality analysis on L-Town. As seen in Figure 3, there are no discernible differences between the pressure-dependent system and the constant demand system. This may indicate that the pressure-dependent demand analyses may be unnecessary when looking at water quality for smaller systems of less than 1,000 nodes. However, these are preliminary results, and more investigation will need to be done to ensure the validity of these results. Overall, we have shown that WINTER Simulator in the WINTER Python package is a good way to model water distribution system hazards. Water quality changes in systems with pressure-driven demand are similar when compared with constant demand, and this process can be used to model realistic hazard scenarios and help improve existing distribution system resilience. There's still a lot of work to be done in the future, but introducing this concept will encourage researchers to consider the complexities of real-world water distribution systems during their modeling of disruptive events. At the end here, I would like to take a moment to thank Dr. Ranji, Dr. Kumar, and Dr. Brill for being wonderful resources during the research process, and a huge thank you to Dr. James Lewis, without whom this project would not have been possible. Thank you for listening.